Limits number 8 is about what's called the squeeze theorem. And the squeeze theorem allows us to find values for limits that we otherwise would not be able to find. And it also gives rise to two important trig limits that we're going to use. Also, there is no Delta Math assignment for this, so your homework is strictly just the limits number 8 worksheet. The concept behind the squeeze theorem is pretty easy to follow. What it says is if I have a function g of x and its y values fall in between two other functions that I'm calling f and h. So in my picture here, here's f of x and here is h of x. And notice that g's y values fall in between those two. And if the limit as x approaches a of f, and if h, as I approach a, if they have the same limiting value, that means g is forced to have that same value as well. So let's see how it works. I have an example here. We're going to use the squeeze theorem to evaluate this limit. Notice that direct substitution into this limit will not give me an answer because this is going to be the cosine of 10 divided by 0. And what is that? I don't know. So what I'm going to do is just kind of focus on this part for right now. And what I know is cosine values will always fall between -1 and 1 inclusively. So I'm going to start by saying precisely that the cosine of 10 over x has to fall in between -1 and 1. And so now I'm going to multiply everything by x squared. And it's kind of important to note that x squared, no matter what my value of x is, whether it's positive or negative, what I know is that x squared will be greater than 0. It will be a positive number. What that means when I multiply the three parts of this inequality by x squared, it's not going to switch around these inequality signs because I'm just multiplying by a positive number. So here I'm multiplying each part of my compound inequality by x squared, and it gives me this statement right here. And my next move is to find the limit as x approaches 0, because that's what I'm trying to find right here. The limit as x approaches 0 of each part of this compound inequality. And now I'm going to evaluate each one of these limits on the left and on the right. And to evaluate the limits, I'm just going to do a direct substitution. So the limit as x approaches 0 of -x squared is simply just going to be 0. And the limit as x approaches 0 of x squared by direct substitution will also give me 0. And because this middle part of my inequality falls in between 0 and 0, then my limiting value, what I'm trying to find, this was my original question, is forced to be 0. Therefore, my limit as x approaches 0 of x squared cosine 10 divided by x equals 0. And this is my answer right here. And I went ahead and brought a graph in so you could visually see what's going on. So here is a graph. And the red one right here, this is y equals x squared. This is negative x squared. And the blue one here is the graph of my x squared cosine 10 over x. And you can see that the blue graph stays within the bounds of the red and the black one. So since their limiting values of the two quadratics is 0, because my cosine graph is squeezed in between those two, it also has that limiting value of 0. And here's one more example of the squeeze theorem. Here in example 2. So I've got my three functions, f, g, and h, and they're structured like this. And I'm given f of x and h of x, and I have to find the limit as x approaches 1 of g of x. Notice I don't even know what g of x is, but I'm just going to go ahead and set it up as this inequality indicates. So I've just put them in this order right here, and now I'm going to do the limit as x approaches 1 of each of these three parts. And my next move is going to be to evaluate each of the two limits on the left and on the right, and I'm going to do that just by doing a direct substitution. So I'm just going to take the 1, plug it in for the x's, And that gets me to this step. And now I'm just going to calculate these numbers right here. So I've got 2 minus 1 plus 5, which gives me a value of 6. And calculating on this side, this is cosine pi, which is a -1. So this is going to say 4 minus 2 times -1, which is going to give me a 6 on the right side as well. And because the limit as x approaches 1 of g of x has to be in between 6 and 6, that means it has no choice but to equal 6 as well. And so the limit as x approaches 1 of g of x will equal 6. Next up, we have two important trig limits here. And they can both be proved by using the squeeze theorem. You've got the proof of one of them over here. And I just have the graphs set up for you. So I've got my cosine x is this red one, and y equals 1 is the green one, and sine x over x is this blue one. And you can see since the cosine and 1 both have a limit as x approaches 0 of 1, that forces sine x over x to equal 1 as well. So I wouldn't get too hung up in the proof of this. Just from this point, just know that the limit as x approaches 0, sine x over x equals 1. And over here, I've got an extension of that. So we can extend it as long as you have the same coefficient in front of each one of these. Whatever that number is, as long as it's the same, that limit as x approaches 0 will equal 1. And then I've got a second one down here as well. This one can be proved using the squeeze theorem, but at this point you can just kind of memorize it so that you know what it is in case you're called upon to use it. As you might have guessed, looking at these 4 examples down here, they all involve the sine trig limit. It is the more popular of the two. So I'm going to take a look at this first example right here. First, realize that direct substitution is going to get me nowhere because it's going to be 0 plus sine of 0 is 0 divided by 0. I have my dreaded 0 over 0. So direct substitution falls through. There is no factoring to do, so I can't use my factoring method. So what I'm going to do is, especially since I see this right here is very attractive to me. So I'm going to use this limit that I established right here. So I'm going to use some of my algebra skills to isolate the sine x over x. And my plan is to give this denominator to each term in the numerator. So I just took the 3x over the x, and I took the sine x over the x, and I came up with this. And now because of properties of limits, I know that I can do the limit as x approaches 0 of each one of these independently. And for this part, those x's cancel out, and the limit as x approaches 0 of a constant is just that constant. So this part is 3 plus. This is what we have above, and we know the answer to that is 1. And 3 plus 1 is 4, and that is my answer to number 1. The idea with number 2 is pretty much the same. I want to use some algebra and try to get that sine x over x isolated. The algebra is a little bit different on this one, and when I look at it initially, I might not know exactly what to do, but what I see is that here in the denominator, I have a common factor of x, so let me factor that x out. And once I do that, it gives me a little more direction because I see this sine x over x, which is very attractive to me. So I'm going to use some algebra and try to isolate that. So I split it apart like this, and I wanted to get that sine x over x by itself so that I could use that theorem that I have above here, that limit as x approaches 0, sine x over x is 1. And I'm going to use the property of limits that says I can evaluate each one of these separately. So I'm going to split this apart. So now that I've got it split apart, I can evaluate each limit separately. I know that the limit as x approaches 0 of sine x over x is just going to give me 1 times, and this limit over here is x approaches 0. I'm just going to do a direct substitution to evaluate that one, And I'm just going to take the 0 and plug it in. And that gives me 5 halves. And 1 times 5 halves is 5 halves. And that is my answer. The concept in examples 3 and 4 is pretty much the same. So I want to be able to get number 3 to a point where I can use that theorem that I established above. And I've written it right here so we have it in front of us. And I'll be able to use this when I can get these coefficients to be the same. So I need the coefficients here to match. And right now they don't. So this says 2x, but down here I just have a 1x. So what I would like is for there to be a 2 right here so that I can use that theorem. So what I'm going to do is force it to be a 2 by multiplying this by 2 over 2. And that gives me this. Notice that when I multiplied the numerator by 2, this did not become a 4x. It doesn't work like that. It just multiplied the sine of 2x by 2. But notice that what happened by doing that is I have now generated that sine of 2x over 2x. And I've made it match up to what this theorem up here says. So I know this portion of it here is going to be a 1. So just so you can see that property in action, what I did was I took this constant multiple here and I pulled it to the outside. We had a limit property that said we could do that. And then the remaining portion of this is just going to equal 1. So this becomes 2 times 1, or simply just 2. Go ahead and try the next example, and I'll help get you started on it. So when I look at this, what would make this nice is if these two coefficients matched. So think about what you can multiply by to get those two to match. So if I want this denominator to be a 12 to match this 12, I multiply by 6 over 6, and then my limit becomes, the limit as x approaches 0 of 24 times sine 12x over 12x. Notice again I multiplied the 6 times the 4. I did not multiply the 6 times this 12 right here. And then I'm going to do what I did before. I'm going to take this 24 and I can pull it to the outside of the limit. And now I've got this limit as x approaches 0 of sine 12x over 12x. I've got it in the format that I need in order to use that theorem, and that these are both 12. So I know that this entire value is going to be 1, and 24 times 1 is going to be 24. And just a couple things to look out for when you use these. Number one, make sure that before you try to use that either one of those theorems, that x is approaching 0. Notice x is approaching 0 in all of these. And also make sure that your algebra is spot on. It's easy to mess up algebraically, so just be on top of that.